Section 1.4 will be all about set operations. And the first two set operations we'll talk about are the union and intersection operations. For sets A and B, we defined first the union, A union with B, as the set of all x such that x is an element of A, or x is an element of B, or x is in both. We define the intersection, A intersect B, is equal to the set of all x such that x is an element of A and x is an element of B. We can use Venn diagrams to get an idea to visualize how two or more sets along with their unions, intersections, and so forth operate. The Venn diagram shows the sets here as each individual circles, and then we can show the intersections and unions by highlighting different areas within the diagram. So for instance here, the intersection of the two sets A and B, when they overlap like this, will be that area where they overlap with each other. It's all the elements that are in both sets at the same time. The union, it means that we put them both together. It's all the elements in A or elements in B or elements that are in both. So when we combine the areas in the Venn diagram of both sets, this is what we would see in the union. Two sets don't necessarily have to overlap, however. In those cases, we say that they are disjoint. So here's a Venn diagram of two disjoint sets. So when there are two disjoint sets, the intersection is empty, or in this case, we say A intersect B is equal to the empty set. Two other set operations we defined are complements and symmetric differences. For sets A and B, we defined the relative complement of A with B as A with a backslash B, and it's equal to the set of all x such that x is an element of A and x is not an element of B. For the symmetric difference of A and B, we use this, looks like a plus symbol inside of a circle, and that stands for the set of all x such that x is an element of A or x is an element of B, but not both. We also define the complement of a single set, such as here the complement of A, as A superscript C, and that's equal to the set of all x such that x is not an element of A. And that is, in this case, the set is including all the elements that are not in the set A. And we generally will consider the outside of a single set as the set U for the universal set, for which any given set could be a subset of. Here's a picture of a Venn diagram to show what the relative complement of set A with B would look like. It's everything in A except for the part in B. So it's like we take away the overlap of B with A. Here's a picture of what the symmetric difference stands for. It basically means everything in A or B excluding what they have in common. So it's kind of like the union, but removing the part where they overlap, removing the intersection of the two. The complement of a single set means everything on the outside of that set. So I'm drawing here the set A inside of a box, which is meant to stand for everything outside of it. And so shading out the outside of A is meant to stand for the complement of A. How are we going to draw a Venn diagram to illustrate this situation? Well, let's consider first off what B complement looks like in a Venn diagram. B complement is everything outside of B. So I've shaded that in here. And then define the intersection with A. We'll identify the area in common between A and the complement of B. So only this part here that I've drawn lines across represents the area that A intersects with the complement of B. So that's what we would draw to show the area for, in the Venn diagram, A intersect B complement. Everything outside of B that's intersecting or overlapping with the set A. Here's another one. A complement union B. Let's first consider what a complement looks like. So I've shaded in a Venn diagram to show what a complement looks like. It's everything outside of A. And I want to union that with set B. So what that means is we join these two together. We take and we combine the areas highlighted in both of the Venn diagrams. So it looks something like this. Or if I just put it all in the same color, this is what it would look like. A complement union with B. Taking everything from A complement and everything with B and putting them all together. Here's A complement symmetric difference with B. Same kind of situation in a way from the union, just one extra thing we have to do for the symmetric difference. So here we're looking at A complement and shaded in for B. What we do for the symmetric difference is we combine together the area for A complement and the area for B, but we exclude the area that they have in common. So I've drawn lines across here to illustrate the area where A complement and B overlap with each other. So we're going to exclude that area they have in common when we write symmetric difference. So if I take all the area from A complement and all the area from B complement and put them together in one picture, excluding that area that I've highlighted, this is what it would look like. And this is what the symmetric difference of A complement with B would look like in a Venn diagram. Now we can also have three sets as well, say A, B, and C. So now here I've drawn three circles in my Venn diagram to illustrate three different sets. And we're going to do A union B complement with C. So how this works is, first off, let's illustrate what A union B looks like. So A union B would be the two sets A and B put together. So I highlight both sets. To do the complement, relative complement with C, we'll remove that area that overlaps with C. So we're taking away that part out from the union. So how that looks is like this. So we take the A and the B, but we subtract away the area that overlaps with C. And that would be A union B relative complement with C. A lot of properties that held true in algebra will also hold true for set operations, in particular union, intersection, and complement. So I'll highlight a few of them here. One of them is the commutative law. Union, intersection are commutative operations, we can call them. In other words, we can reverse the order, say A union B is the same as B union A. Associative, union, intersection are associative. So for instance, A union with B in parentheses, union with C is the same thing as A union with B union C in parentheses. We can reorder the union operations, either do an A union B first or B union C first, and either way we'll come out with the same thing. That's what we call associative, and it also works in the same way with intersections. Distributive law, we can distribute union across intersection or intersection across union. So for instance, it says that A union with B intersects C is equal to A union B intersect with A union C. So that A union distributes to both the B and the C across the intersection operator. And that's what we call distributive laws. Similarly, you can see that it works for intersection with union as well. The next one is called idempotent laws, and that basically means if you union or intersect a set with itself, you have the same set in return. So A union A or A intersect A is both equal to A. Identity laws have to deal with the empty set and the universal set. So you can see here, if we union with the empty set, we get A. If we union with the universal set, we get U. If we intersect with the empty set, we get empty set. And if we intersect A, intersect U, we just get A. The complement will cancel out in a sense if we do double complements. So A complement is still equal to A. It's kind of like double negation would be with numbers. And then it says here A union with A complement is equal to U. So everything in A union with everything outside of A is the full universal set. And if you intersect A with its complement, it's an empty set because there's nothing in common with what's inside and outside of A. And then the complement of the universal set is the empty set. The complement of the empty set is the universal set. And then the final ones have a special name. It's called De Morgan's Law. De Morgan's Law says that A union B complement is equal to A complement intersect B complement, or A intersect B complement is equal to A complement union with B complement. I'd like to highlight this one in particular and show the Venn diagrams that illustrate how these actually work. So for De Morgan's Law, let's look at the A complement here, everything outside of A, intersected with everything outside of B. If we consider the intersection, which is the overlap of A complement and B complement, what we'll see is this area here, which actually is all the area outside of both A and B. So that's how De Morgan's Law says that A union B complement is equal to A complement intersect B complement. In a similar way, if we look at A complement union with B complement, and we join that together, the only thing that's not brought together by unioning the two complements is the bit in the middle where the two sets overlap. And that's A intersect B complement. So that's how De Morgan's Law says that A intersect B complement is equal to A complement union with B complement. Now what we're going to do is look at some examples with sets and talk about the intersection and union and other set operations based off of these sets. So for instance, we have A defined. So here we have a definition for A, for set B, for set E, and we're going to do some work with those. So let's start out by listing out a few elements or every element depending on how many there are from each of these sets. So looking at set A, it says it's the set containing all n in the natural numbers such that n is less than or equal to 11. So what that would look like is 0, 1, 2, 3, 4, 5, and it's going to go all the way up to 11. Okay, so that's what set A contains. Set B, it says, is all n in the natural numbers such that n is even and n is less than or equal to 20. So this would contain elements 0, 2, 4, 6, and we're going to go all the way up with even numbers up to 20. And then let's go ahead and list out set E. This is just all n in the natural numbers such that n is even. So that's going to keep going forever. It'd be 0, 2, 4, 6, 8, and so on. Okay, now with that in mind, let's look at A union with B. We looked at this in the Venn diagrams, but in this case, union again means to join the two sets together, take everything from A or everything in B or in both, and put it all together. So if we do A union B, we'll take all the elements from A along with the elements from B. So it would look like 0, 1, 2, 3, 4, 5, pretty much consecutive numbers here, 7, 8, 9, 10, 11, and then it's going to go 12, 14, 16, 18, and 20. Now if we look at A intersect with B, A intersect with B are all the elements in A and B. So only the elements that they share in common. So looking at the sets, the elements that they share in common would be basically the even numbers all the way up to 10. So the A intersect B would contain the elements 0, 2, 4, 6, 8, 10. Okay, if we look at the next one, which goes A union with E. Now we're going to take all the elements in A and union them with the elements in E, put them together. So it goes 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and then that's all from set A, and then it's going to bring in all the other elements from set E, which will be more even numbers. So 12, 14, 16, 18, and then it'll just keep on going from there. If we look at the intersection of A and E, well, it's going to be very much just like we did with A and B, pretty much. The intersection of A intersect E would just be 0, 2, 4, 6, 8, 10. To go back to the relative complement, symmetric difference, and complement, let's look at a few examples of those. So looking at the first one here, asks for A complement with B. Okay, so that means we're going to take everything in A, but remove anything that it has in common with B. So whatever elements in B that are in A, those are going to get taken out. So the elements in B that would get taken out of A would be the 0, the 2, the 4, the 6, the 8, and the 10. So A with relative complement and B would contain the elements 1, 3, 5, 7, 9, and 11. Now if we do the other way around and do B complement with A, now we're going to take away the elements in B that it has in common with A. So that means we're going to take basically the 0, 2, 4, 6, 8, 10, and those will be removed because those are coming away from set A. So the set B complement with A would contain 12, 14, 16, 18, and 20. Next one says A relative complement with B. Okay, now for this one, we take everything that is in A combined with everything that's in B, but take away everything that they have in common. So let's highlight what they have in common here. They have a 0, 2, basically all these even numbers up to 10 they have in common. So those will not be included in the relative complement, but we will include all the other values here. Everything else gets joined together in the relative complement. So it would look like 1, 3, 5, 7, 9, 11, and then 12, 14, 16, 18, and 20 would be the elements contained within the symmetric difference of the two sets. Next, we're going to do E complement with B. So that means we take everything in E and exclude the value, take away the numbers from E that are also in B. So if we look at the numbers in B, they're all the even numbers up to 20. So keep in mind that E keeps going up with numbers up to like 18, and then 20, and then 22, and then 24, and then it just keeps on going from there. If we complement with B, that means all those elements from B are getting removed from E. So that means we're going to take away all the even numbers up to 20. So E relative complement with B would contain the elements 22, 24, 26, 28, and then it just keeps on going from there. We want to take it a step further. We could even write this in set builder notation. This would be the set of all n in the natural number set, such that n is even and n is greater than or equal to 22. Now let's do the complement here of the natural number set complement with E. Okay, so that means we're going to take away all the numbers from the natural number set that are contained within E. E contains the even values, if I scroll back up here, all the way from 0 off from there, so all the even numbers in the natural number set. If we complement that, we're going to take away all the even numbers, which would leave us with just the odd numbers. So natural numbers complement with E would be the set containing 1, 3, 5, 7, 9, and it would just keep going from there. Or in other words, it would be the set of all n in the natural number set such that n is odd. Let's look at A, symmetric difference with E. So again, how we think about symmetric difference is we think of everything in A or everything in E, but not what they have in common in both. So if we go through and we highlight the numbers that A and E have in common, it's basically going to be, again, here just even numbers. So we'll join together everything from A and join it together with everything in E, but exclude the numbers that we see here that they have in both at the same time. So A symmetric difference with E would contain the elements 1, 3, 5, 7, 9, 11. Okay, and then it's going to pick up from there with elements from E, which would be 12, 14, 16, 18, and so on from there. Okay, and then let's look at one more here that goes A union with B, intersect with E complement. Okay, so before getting started, let's again write down what A union B is equal to, and let's think about what E complement would contain. A union B would be 0, 1, 2, 3, 4, 5, and we'll just write them all the numbers out here. So A union B looks like both A and B put together. E complement, that'll be all the natural numbers not contained inside of E. So E contains all the even natural numbers. So E complement would be all the odd natural numbers. Now let's do the operation over here of A union B intersect with E complement. We see A union B, and if we do the intersection with E complement, we'll just take the numbers they have in common. So we see 1, 3, 5, 7, 9. So those are the values of the intersection between these two sets. So this set would contain 1, 3, 5, 7, 9, and 11. Let's consider how these operations work with intervals in the real number set. So let's look at the interval here, closed interval from 0 to 2. That would be equal to the set of all x in the real numbers, such that 0 less than or equal to x less than or equal to 2. Or in other words, on the number line, it would look something like this here. And we're also going to look at the half open, half closed interval from 0 to 1. That would equal to the set of all x in the real number set such that 0 less than x less than or equal to 1, which would look something like this if we consider the number line. First one we're going to look at is the closed interval from 0 to 2 with the relative complement from the half open, half closed interval from 0 to 1. Well, in this case, how it will work is we'll look at the interval from 0 to 2, and we'll take away that interval from 0 to 1. So inside of this interval is that interval from 0 to 1. So if we take away that stuff here in the middle, everything that will be left over would be between the 1 and the 2. But also keep in mind that since there's a parenthesis there, it doesn't actually take away the 0, since the parenthesis means that the number is not included as part of the interval. So what that means for us is the interval here would be a singleton set for 0, since 0 will be left over after taking away the other interval, union with the interval open from 1 to 2 closed. So that inside interval, when it did the complement, it took away the interval from 0 to 1, but did not take away the 0 because of the parenthesis. Did take away the 1, however. So when I write the final interval from 1 to 2, I have to put a parenthesis at 1, but I can still close it up at 2. If we consider the intersection of these two intervals, now consider where it intersects with that interval from 0 to 1. Well, that's going to be on the inside here of the bigger interval. So it's going to intersect in the interval from parentheses 0, 1. Let's consider the symmetric difference with a closed interval from 0 to 2 and the closed interval from 1 to 3. Now we have to think about what the symmetric difference tells us again. It means to put them together but exclude the part that they have in common. So if we consider the interval from 0 to 2 inside there, and we consider the interval from 1 to 3, then notice how they overlap here in the middle. We're not going to include that overlapping piece, but we will include everything else combining the two intervals together. So when we exclude the part from 1 to 2, that's going to give us an interval bracket 0, 1 with a parenthesis, since 1 has been removed, union with the other interval, which is going to be parenthesis 2, 3 bracket. If we look at the 0, 2 closed interval, but complement of that interval, what would that stand for? Well, the complement means to take everything on the outside of the set. So that's going to be the outside of this interval. So if we shade that in, it's now going to be going the other direction. And that would be the interval from negative infinity to 0, parenthesis, union with parenthesis 2, infinity. Now if we consider this particular intersection with the closed interval from 0 to 2 and the interval from negative infinity to 1 bracket, the interval from negative infinity to 1 is going to come up to here. We want to find the intersection or the overlapping piece. So that's going to be this piece here in the middle where they intersect. So that would be the interval from bracket 0, 1, close bracket.